Awesome. Awesome. Welcome, everyone. This is our second meetup for Deep Learning Adventures. I'm George Soto. I'm happy to be here with you today. I have many friends of mine from other meetups. We found it was overdue for us to have an online event where we talk about deep learning, and specifically taking a course on Coursera, like you see in front of you, this TensorFlow and Practice Specialization. That's our first adventure. And going through it week by week, and meeting online and discussing what we learned, what we found challenging, what we found interesting, and things of that nature. So our first meetup was last week, and on our meetup page you can find the links to it. Let me make this present. I received some feedback from our last session on what exactly did we talk about, and I added 2 extra slides on the first presentation, which you can find again on the first meetup. But basically, and also on the Slack, you can also join us on Slack. What I'm showing here is basically a very simple neural network which accepts 2 features or 2 inputs. It has one hidden layer with 4 nodes, and it has an output layer, sometimes also called as a second hidden layer. Some people call it an output layer. So I was admitting one more person there. That applies some kind of linear combination of its input. All these nodes apply some kind of linear combination of its inputs. You see that by the way, W. And the input plus a bias. Then some kind of nonlinear function that is called an activation function. That could be a sigmoid function, it could be a ReLU function, it could be a leaky ReLU, there are different activation functions that you can apply. And then based on the output of that activation function, if this is the output layer, you can make some kind of a threshold decision. If it's more than, in this case, if it's a sigmoid, you know that's between 0 and 1, you can adjust the threshold to be 0.5, and if anything is more than 0.5, then you classify the input to belong to one category out of 2. If it's less than 0.5, you classify it to be in the second category. So let's say cats and dogs. If your output is more than 0.5, then you classify it as cats. If it's less than 0.5, you classify it as dogs. In our first session, we had actually, let's go to the next slide. So in our previous session, we had the challenge of fitting a line. So basically, we had numbers here, one-dimensional numbers. We didn't even have 2 features. We only had 1 feature, and the numbers were -1, 0, 1, 2, 3, 4, and the output was the y's were basically a linear combination of the x's, and I think the equation was 2x
-1.
-1, yep. So then in our feed model here, we trained our network, and what that network basically did is, since you only had 1 node, you would have one weight variable and 1 bias. And what I'm showing this graph here is how does that weight and bias variable changes as this model.fit progresses, basically as our network learns how to fit the x's to the y's. And you can see that in the beginning here, it starts with some random W and some W and some random B. In this case, negative 1.2 and bias 0. And then as it progresses, somebody is joining. As it progresses, the bias, the weight, becomes less negative. It becomes positive, 0.3, 0.4, 0.5. And the bias as well increases slightly to 0.3. So eventually, if you let it train for longer, this will come very close to 2x. I don't remember if it was +1 or -1, but eventually will become very close to our line that we had defined. Okay. Any questions here on what does this graph represent, or what does it mean? I just wanted to clarify this. You can unmute yourself, or you can text on the chat box.
That's very cool, George. How did you get it to print out the weights and bias at each at the end of each epoch?
Yeah. So we'll cover that today. There is so in model.fit we have a function called callbacks. It's an argument.
I see your get. Yeah. Okay.
So you have you can define your own callback, and basically what that does is you can specify either at the end of each epoch or at the end of each batch. There are different methods you can specify. And what I basically did is I tried to figure out what is the weight and what is the bias, and after each epoch, just plot them on a graph like this.
Excellent.
Yeah, that's today. Awesome. Okay, so then we'll start with, if there's no other questions, we'll start with today's presentation. Again, feel free to unmute yourself and participate if you have any questions. Awesome. So the second one, there's again the link here, the GitHub repository, the Slack channel, the YouTube recording from session 1. Feel free to go over it in case you missed it from last time. And once tomorrow, when this is updated, I'll update the slides as well for the recording for this session. Again, a reminder, this is not a typical meetup. We'll be playing a trivia game in the end. I'll be showing this very slide in the end as well. But if you open a new tab right now, and if you go to joinmyquiz.com, you'll be asked for a participation code. You can enter the code 299901, your name. Again, we'll visit this in about 45 minutes based on our progress. You'll see this again. It was very fun last time. It was exciting. Heard a lot of good feedback, so we'll do that again today. Just a reminder that the slides and some of the material we'll be looking at are coming from Coursera and Deep Learning. They're not my materials, so I'm paying attribution to their content here. Somebody's joining us. And what is this specialization again? So this specialization is called TensorFlow in Practice. It assumes a little bit of a knowledge of basic deep learning. Should be a little bit familiar with what are features, what is a hidden layer, what is an output layer, what is an activation function, what is a loss function. Not in detail by any sense, not in any mathematical prestigious understanding or like able to read papers, but some kind of understanding maybe from online courses, like many of us here have taken Andrew Sang's deep learning specialization. That actually covers, from what I've seen so far, everything in this specialization. Like the new part in this specialization is how do you actually make this work in TensorFlow, so the programming part of it. And Lawrence actually explores this. If you take his course, you'll see that he comes a little bit more from like a developer perspective. So he understands the challenge. He doesn't dwell a lot in the theory and the math behind it. He just says, this is my challenge. I have images of human and horses. I want to just build a classifier that with minimum effort, just 5 lines of code can classify humans from horses. If TensorFlow is your programming language in your day-to-day job or activities, there's a more advanced version of this called TensorFlow Data and Deployment Specialization. I haven't taken it so far, so if this is to a beginner level for you, please check this one out. So the one that we're taking right now, this TensorFlow Specialization, has 4 courses, and today we're focused on the remaining of course 1. Meetup 1 was the first week of course 1, and meetup number 2 today is the remaining weeks of course 1. I thought we'd give it a try to group them together because as you'll see, week 2 and week 4 are pretty short. Week 3 to me was the longest one, and we'll take a look. A reminder that I recommend you use something similar to Colab. Colab is a Jupyter notebook on Google Cloud. You don't have to spin up your own resources. They give you a free lightweight VM for free. You can even set it up that it uses GPU or TPU. And all you need is a Google account and a Gmail account, and you can save all your work, share it with others, and things like that. Awesome. So a reminder in terms of agenda and map where we are. So last week we covered week 1. Today, hopefully we'll cover as much as we can from week 2, 3, and 4. And again, week 3 to me was the most challenging, or the longest one in terms of programming. Cool. So week 2 starts with a new data set, this fashion MNIST. This fashion MNIST, think of it as the MNIST database with the digit 1 base, but with fashion items. So you can see here you have clothes, you have t-shirts, trousers, pullover, dresses, coats. You have 10 categories of different items. There are 70,000 images in this database, or in this data set, and 10 categories. The images are heavily processed and they're scaled to 28 by 28 pixels, and they're in grayscale. So there's no color here, it's only one channel. And the challenge is, can we train a neural network that can classify an input to one of these 10 categories? And on the right here, this 3D looking object is basically a representation of this data set using something called Tisney. I have a link here from Wikipedia. It's a paper that Hinton came up with a long time ago on distributed stochastic neighbor embedding. Think of it as when you work with neural networks, the main feature that a neural network does is try to represent items in a higher dimensional space. What this Tisney module does is it takes those higher dimensional spaces and it tries to represent them in a 3-dimensional space so that we as humans can understand, relationship, and also tries to preserve some kind of a distance metric so that, for example, all the shoes are closer to each other, all the shirts are closer to each other, all the sandals and so forth. I have a link to the fashion MNIST dataset here on GitHub, and this is a sample image here that you see. It's a 28 by 28 grayscale, and the values go from 0 to 255. 0 is the lightest version, there's no content. 255 is the darkest, meaning there's a lot of content there. Cool. So how do we use now TensorFlow to actually read this data set and do some kind of classification or of different input images? So we need 2 packages. We need TensorFlow SDF and TensorFlow. From TensorFlow, we need to import this Keras API. Then Keras API has an attribute called dataset, and that dataset, as you can imagine, you can find different datasets. Fashion MNIST is one of them. So if you just type datasets.mnist, you're going to get the MNIST dataset. If you type fashion MNIST, you're going to get the fashion MNIST dataset. And if you look at it, it's actually a repository, Python repository.
Released iOS 13.4.1 a couple of weeks after the release of iOS 13.4. Now, this also comes 1 week after the release of iOS 13.4.5 developer beta 1. So, like I said in that video last week,
do you mind muting yourself for some reason? I
iOS 13.4.5, but iOS 13.4.1, 0.2, 0.3, and 0.4 will all be public releases that do not need.
Okay, you can do it, George.
I had to kick him out. I was trying to mute it, but I couldn't. Hopefully, he doesn't get offended. So then, from this MNIST object, we can call this method called load data. Sorry, I see something in the chat as well. Good. Oh, perfect. Yeah, if you see anything in the chat, please reply or let me know. And from load data, we basically get 2 tuples, or 2 collections. One is the training images and training labels, and the other one is the test images and the test labels. And the training images, again, are 60,000 of them, and test images are 10,000 of them. And the next few lines, we do something called normalization. Instead of taking the values from 0 to 255, we divide them by 255 so that the range of the content now is between 0 and 1. We do this for various reasons. One of them is we don't want the network to fixate too much on bright parts of an image. Let's say to a simple network, an image of a shoe, an image of the same shoe, but with high contrast is a completely different item. It will probably classify it as something else, given that it looks at individual pixel values. So if we want to somehow hide that contrast feature, which for us humans is very easy to forget about, but for a machine it's a very high number. We divide it by 255. And I don't know if anybody knows any other reasons why we do this normalization. I know it has to do with input distribution and things like that, but any other perspective? I'm curious to hear what other people have thought.
Isn't that just normalizing the number to 0 to 1? because the values are, yeah, up to 255.
Yeah. Okay.
I suppose it wouldn't really matter to normalize those, but it all depends on how you initialize your weights and how quickly you'll end up training. With most of the standard assumptions, you want data that are not too far from zero, between -1 and +1 is a good.
Is it to make it less complex?
It's to make it so that the training process takes a reasonable amount of time.
Okay.
Yeah.
And is stable.
Okay. Thank you.
And also to avoid some kind of like contrast bias. Let's say for some reason all your shoes are really dark in content, but all your bags are really bright in content. I think you might do really well in one class, but not the other. I think you might be really well in the bright category, but not the dark category. So just to avoid some kind of a contrast bias, to me, that's the main reason why I do this, as well as Robert said, for faster training.
Oh, thank you, George.
Yep. Awesome. So then after this scaled version of the images from 0 to 1, again, these are real numbers or float numbers in TensorFlow. We define a simple dense network here and a sequential network, sorry, here. A sequential is basically a stack of networks or different layers stacked after each other. So we start with flattening our input. We talked about this last time. We have a square matrix right now, 28 by 28. We need to convert that to a vector so that our input is basically a 28 by 28, which is 748 numbers, is a single vector that is fed to our model.
George, this is Kathleen.
Okay.
Hi. Sorry to go back to the division by 255, but if you're dividing everything by 255, that doesn't do anything. I mean, it's just like adding a constant weight in there for everything. Oftentimes they'll do histogram equalization, so they take each image and divide it by its own range, and that would stretch things that were where if most of the image was way dark, it would stretch it. But
yeah,
I don't see that dividing by 255 every single image. I don't see that it does anything at all. Am I missing something?
I mean, it certainly has no impact on what the global minimum or what the optimal values of the weights and biases are, right? It doesn't distort the image. It doesn't change the relative values between pixels at all.
Exactly.
But
the relationships are all the same. I mean, it's just where you squished it, what the range is.
Right.
But if you did them differentially, like each one, you forced each one to.
Are you thinking something of dividing or reducing the mean and dividing by the standard deviation?
Yeah, well, I mean, typically when you're doing this, you do a histogram equalization in the beginning, and that keeps you from getting distinctions between the histograms of the individual images, which could have to do with the lighting when you captured it, or something else. You don't want to just say this is the darkness of the image to decide
yes,
this is a shoe and that's not a shoe.
Mm-hmm.
If they're both shoes, but one has got just a brighter histogram. So this was in the slides that you got from the course, right?
yes.
Yeah.
So one of the really cool things about deep learning and this field in general is that you can play with these things on your own, and many of these questions, when you go through this course, like so many more, when I've gone through the first couple weeks, so many more questions have come through my head than what the course materials necessarily bring up, and you can just start trying to answer these questions. So yeah, if someone does want to play around with the the 255 and see how that affects things. I'd be curious to hear your experience.
Yeah, actually, one of the exercises later on just plays around with this very model and changes different things and looks at the output. Cool. Okay. In the interest of time, I'll move along. Good.
Just I think Robert was probably on the right track when he said it had to do with, it does make you converge a lot faster. It has to do with the initializing the weights, the assumptions made.
Mm-hmm.
But I was just going to say, it's a very standard thing in all image, visions type of neural network work with convnets to rescale the images, the pixels by 255. It's to make them go between 0 and 1.
Mm-hmm. Yeah, maybe we can do a bit of research later on. I saw somebody posted on the chat, Jay, here, some resources online. Maybe can visit this next time. I'm curious as well. Cool. So then the simple network here that we define is a fully connected layer network. It has 2 layers. One that maps our input, which is again a vector of 748 numbers, to 128 numbers, and from 128 to 10. 10 because our outputs are actually 10, so we have 1 neuron giving us an output for each of the 10 classes. Then we also, the next step in TensorFlow to actually make this work is to call model.compile. You specify what is called the optimizer, which is basically how will the weights be updated and how will the model give you new and improved guesses. So in this case, we're using an Atom optimizer. We also want to measure how far are the outputs of our model from the actual labels. And there are many loss functions here. I have a few links here for different loss functions. In this case, since we're using categorical outputs, we're using labels from 0 to 9. We use a categorical cross entropy. There's a binary version of this called binary cross entropy. And there are a few other ones that I'd love to, dwell deeper, maybe from TensorFlow perspectives, maybe in another session. But I have a few links here from the Kera's documentation of sparse categorical cross entropy. Your target should be integer targets. If you have categorical targets, like shoe or something else like text, maybe, then you use categorical cross entropy. And there's a link here for multiclass log loss on its link. Then what are we trying to optimize here? We're trying to optimize the accuracy and basically how many of the labels did our network get correct. And then the actual model that does the training is the actual method that does the training is called fit. So we call that on a model.fit. We give it as input the training images and the training labels. And we specify a few other parameters, for example, how many epochs this network should train. And then we just let it train. And then here you can see the output of this model.fit. It goes through each of the 5 epochs. It tells you what is the value of this loss function based on this sparse categorical cross entropy method, and what is the accuracy. So out of the entire 60,000 images in our training set, how many did we get correct? We got 82% of them correct, just with 1 epoch. Sorry, that was a question. Okay. Then how does this image, let's look at one sample image. How does it look like? So if we plot it, if you pay attention, this is the image. This is the image in represented in numbers. You kind of see the shape of this sandal, I guess. It's kind of interesting to see. Then what I wanted to show here is how do you actually evaluate? So how do you take now a test image? So you call the model.evaluate. You take a test image. In this case, let's say this one. Sorry, that's prediction. In this case, sorry, we want to evaluate how does our model behave on a data set that it has never seen. And this test image is actually the data set of 10,000 images that the fashion MNIST has for testing. So we train our model on 60,000 images for 5 epochs. Now we want to see how does it compare to a data set that it has never seen. That's the test images data set, the taste level. So we do that and we get a loss value of 0.07, which compared to our loss value of the training data set is 0.2, looks much smaller. Trying to remember here, was this the loss or was this the accuracy? It says loss. Maybe I didn't include the accuracy as well, but I'm more interested in the accuracy instead of just the loss. There's a few more other screenshots later. Maybe we can look at that. And if we want to look at the output of just one example, there'll be 10 numbers. And if you want to look at the one that we pick, is usually the one that has the highest probability, since this will be treated as probabilities, and that will be labeled 7.
So George, it looks like on the bottom left there, you're doing an average of all the, so you're doing the history, you're doing the average of all the epochs?
Yeah, so
instead of the last loss and the last accuracy?
Yeah.
So that's why it's probably different from.
Yeah, right here, I didn't save the output of the model.fit anywhere, so it just gave me the epochs and the loss and the accuracy for each epoch. But if you store the output of model.fit in a variable, and if you do that variable.history loss or that variable.history accuracy, you're going to get all those values for each epoch. And in that case, we're just doing an NP average here to get the average loss and the average accuracy.
Right.
But that's still on the training data set.
Right.
Awesome. So if you put everything together in one slide, it's just a few lines of code and TensorFlow. Sorry, this should be fashion MNIST. And then you load the data, you normalize them. Make sure that I had an issue earlier today. For some reason, I didn't specify this by default, this input shape for flatten. And one day was working fine. The other day when I was looking at model.summary, I was not getting the expected values. I was getting something called multiple values. So then I did a little bit of digging around and I saw that I had to specifically specify the flatten one. That's one of my questions I have later on. And the same network, optimizer loss, fitting, evaluating, and predicting one image. So this is our basic setup for fully connected layers tackling a computer vision problem. Then this week, this program exercise actually tells you or encourages you, like we talked about earlier, of trying different versions. So experiment, for example, with different values for the dense layers. So instead of having 128.10, maybe you can have more or less instead of 128. You have to have 10 and you have to have 28 by 28 because that's your input and output. Your input is 28 by 28 and your output is 10 categories. You can't change that. But you can add layers, you can change their complexity here or their size, or you can change the activation function and see what happens. If you remove the flattened layer, if you do this in your program exercise, you'll get an error because your input is a square, a 2 by 2 or 28 by 28 input, and your model expects a vector. And what would happen if you had a different amount than 10 outputs? I don't know if anybody tried this. Instead of 10, you say you had 5 or 12. I tried a smaller number and I got an error as well, that for a label that was beyond that value, let's say I had 5, a label that was beyond 5, the network didn't know what to do with it. Then, yeah, the impact of training for more or less epochs, instead of 5, you can do 3 or 15 or 30. You'll see usually the more you train it, your training scores will be pretty good. By scores, I mean low loss and high accuracy. But you might get into a situation called overfitting, where you basically memorize the entire training set and you do really bad on the test set. And then the impact of removing normalization, as we talked about before, I didn't see significant difference, maybe decimal difference in loss and accuracy, but I didn't see any significant difference. Any other questions before we move on? Or feedback or comments?
George?
Yes.
This data set, is it balanced, imbalanced, and how would you deal with it if it's imbalanced?
I think this is balanced. I think the number of images you have for one of the 10 is pretty balanced. If it's not balanced, there are different techniques. You can do oversampling of the imbalanced one, or you can do undersampling of the most popular class. There are different techniques. This is pretty well balanced data set though.
Right. Yeah.
Awesome. And going back to your question, David, I had in the beginning, let's say you define an epoch, a very high number, let's say 30, but you don't want to wait for 30. You just want to say, okay, train my network, and if my loss value in my training set reaches a threshold, or if my accuracy value reaches a threshold, just stop training. And that's exactly what Keras callbacks does.
Mm-hmm.
And that's an argument. So when you call fit, you have your input image, your input labels, how many epochs, and now you have this argument called callbacks, and that needs to be actually an object. That object, you have to define your own class that extends TF Keras callbacks callback. And there are different methods you can define in this class. One of them is called onEpochEnd. There are a few other ones that you can do before each batch, after each batch. There are many methods. This is the most popular one. Basically says, when you're done looking at an entire training set, like one epoch, do this. And what do this means is you specify it here. You also have access to this variable called logs. And from there, you can get loss, or you can get accuracy, and you can do simple comparison. I noticed in the course, Lawrence uses the term loss and accuracy pretty interchangeably. To me, they're not interchangeable. For me, this is the loss that you get from your network, and it's a different metric compared to accuracy. But you can get, instead of loss, you can get accuracy. And if that accuracy, let's say, is higher or equal than 0.8, you can do self.model.subtraining equals true. What that will do is if you see in this example, we're making a decision on the loss value being less than 0.4. So after one epoch, it was 0.47. After two epochs, it was 0.36. That will call this callback. It will check if it's less than 0.4. Yes, it is. It will display a message, and it will actually stop training your model. So you stop training after two epochs instead of waiting for more. And this is what I used before, David. Yeah, on our GitHub, I have the code for the previous one as well. Here I'm getting, instead of logs.get, you can actually call the entire model here. Self.model, and can get the weights and the biases.
Right.
Awesome. Any questions about this?
George, I have as I always do, a little bit off topic, but it's kind of a higher level thing.
Okay.
I love working with Keras compared to the other ones because it's straightforward. Does anyone know, and does Keras break down as sometimes higher level things do, like MATLAB and things like that, where you might have to use TensorFlow, the older TensorFlow API, the more, that's a little bit more complex, but more effective. And I would say roll in PyTorch and all the other ones. So that's just kind of, that's it.
Yeah. So far, I haven't seen it. Maybe in some very advanced cases, there are something you can only do in TensorFlow, but not yet in Keras. Maybe there are some features I could imagine that are only implemented in TensorFlow, but not on the higher version of it, which is Keras. I doubt we'll see this in this course. I don't know.
I agree. You probably won't see it in this course. One thing that I have used in the past that Keras has that I guess it has to be in TensorFlow somewhere, but is that you can make synthetic data. So like with your shoe data that you were showing, there's a feature where you can, it'll take one image and tilt it this way, flip it that way. Mm-hmm. And it actually did improve my training because we had more data. So
yeah, in this course one, you don't do what's called data augmentation. That's what you mentioned. You don't do it here, but I'm pretty sure Keras would have some kind of a data augmentation API.
It does. It definitely does. Yeah.
Okay. Cool. And let's see how far we can go, and maybe we'll see the limits of Keras.
So I would just mention that Keras in TensorFlow 2. I mean, Keras is just a part of TensorFlow. It's not, they're not separate. There used to be, you know, Keras was like used Theano and other backends, but now it's purely part of TensorFlow. They're one and the same.
Mhm.
One place you'll use TensorFlow libraries prior to bringing Keras into your program is often with the data process, especially if you're using TensorFlow data sets. They're very efficient for making very good pipelines of data and things like that to then feed into your Keras models.
Mm-hmm. Awesome.
Thanks.
Then this is just something to tie it back to the very first image that we saw of a simple two hidden layer network. We can imagine this input shape, this flattened layer here, and this dense is basically a very long vector of numbers. And then you can think of this as the problem we're trying to solve is there a linear, or actually I should say non-linear combination of my previous layer inputs that would give me the right label. So in this case, let's say I'm looking at the output. If I look at one layer above, which would be the dense 128, is there some kind of a linear combination of these 128 values that this layer gives me? Can I scale them and pass them through an activation function? They'll give me the number 9. So that's the mathematical problem I'm trying to solve here, you know, under the hood. Something that that I tried working with was Tensor Board. I wanted to use it in, this is optional, it's not covered in the course. I just wanted to share it with you. So we talked about this callback. If you want to use something called Tensor Board, and Tensor Board is basically the UI behind TensorFlow. If you want to have some kind of a visual representation of your loss and of your accuracy over time, use this product called Tensor Board. And the way you do that is you have to specify where would the logs be stored after you train a model, and also a callback for Tensor Board. And when you do that, then you make sure that you call TensorBoard.callback, whatever you called your method here. And then there's a command you can do on Colab. This is called a magic. Anything that begins with percentage in Colab, it's called like a magic command because it's not by default supported. You specify where your logs are and you start it. And basically you'll see something like this on the right. And you'll see how does your model look like, the accuracy, as well as the loss on the training set. And you'll see one line per each time you run it. So each time you run, you're going to get a date and a timestamp, like hour, minute, seconds. So you see how does it improve. So if you want to look at, for example, at here step 3, which is epoch 4. Again, this is 0 based. You can see for different variations, maybe you can do some kind of hyperparameter tuning. You can see how does it look like, how does your loss, in this case, or accuracy value or loss value look like. So again, you want accuracy as high as possible and you want loss as low as possible for your training set. You can do the same if you have a test set as well. One issue that I had with Tensor Board that I'm hoping we can figure out before next time is it has a section called graphs, and that's what I really wanted to use. Think of it as a deep dive version of the model.summary that you look at, where you have all the different shapes of your input and outputs. Here you actually have all the intermediate representations. For some reason now, I'm not able to make it work, and hopefully we can figure it out. You get something like graph could not be loaded if you try it. Again, most of this code is available on Lawrence's GitHub repository. He also mentioned it in his course, so if you want to take a look, I have a link here. Cool. So that was week 2. Any questions before we go to week 3, where we use convolutional neural networks?
So I'll just make a comment for anybody that's actually taking these and doing the exercises. There seems to be a persistent problem when you submit your assignment that there's some JavaScript in the bottom of the files that seems to interfere with their grader. They're actually grade your assignment when you turn it in. Mm-hmm. And it's in a lot of discussion groups. People are talking about it, and I found, I don't know about George, you, but if you just delete those JavaScript cells in your example and then submit, that it goes through just fine. So just seems to be a little hiccup there.
Yep. Thanks for mentioning. Yep. I have a note on it right in the end of questions. Yep. I noticed it though when I commented out, it works. Otherwise, it wouldn't work.
Great. Yeah.
Awesome. So then week 3 actually covers a different model. It doesn't cover your fully connected layers anymore. So it covers convolutional neural networks. And Lawrence and Andrew, they cover this in detail from a higher level as well as from a coding perspective. But to give you an idea, this is one of our images at 28 by 28. This is in this case it's scaled from 0 to 255. And if we want to zoom into this 3 by 3 9 pixels here, you'll see the values. You'll see the higher values are the darkest and the lower values are the brightest. So if we're looking at the center of this is current pixel value is 192. If we look at different neighbors, how many neighbors are on, we look at, you can specify that later in the code. But this is our input so far, or I should say a part of our input. Then the other ingredient we need to make convolutional work is we need some kind of a filter or kernel in other setups. And that is basically some kind of a, think of it as some kind of feature detector. It's not really intuitive as for us, for humans, to see what kind of features is it looking. In this case here on this image, if just by looking at it, I mean the input image and the output image, you can see that it's doing some kind of vertical line detection. So it's really highlighting the lines that are vertical. If you have the negative values horizontally and the positive values horizontally at the bottom, it'll do some kind of a vertical horizontal line detection. I think those are the easiest to understand. There's some complex filters you can define where you can do things like sharpening, blurring, and more interesting combinations. But then how to use this filter? So you take this, in this case, 3 by 3 input, and you take this 3 by 3 filter. And what you actually do is you do a pixel by pixel multiplication, and you add up the entire arguments of this multiplication. So in this case, you multiply 0 by -1, you multiply 64 by 0, 128 by -2, and so forth. You add all these numbers up, then you come up with one value. And now that will be the value in the next layer of this filter applied on this part of the network. And something that you'll notice when you look at the shapes of your tensors, of your data, as it flows from one network to another. If you want to look at your neighbors, think of it if you're the first pixel in the upper left corner, there's no neighbor above you and there's no neighbor on the left or diagonal left to you. So to do that, there are a few ways to do it, to overcome that challenge. You can either skip or not define convolution for that first entire strip horizontally and first entire strip vertically. Or you can do something called padding, where you can basically introduce a new layer vertically and a new layer or row horizontally with zeros. In this course, they didn't do any padding. They just simply started from 1 pixel or 2 pixels to the right, and 2 pixels down. That way your neighbors are fully defined. Then when you do this multiplication again, you come up with these numbers. You do this for every 3 by 3 patch. Then what you do something called pooling. Pooling again is out of all these numbers that you got, somehow you need to reduce or keep only the important ones. And there are different pooling layers or pooling functions you can apply. One of them is called max pooling, where for each 2 by 2 patch in this case, you only pick the maximum or the highest value. You can pick the average. Usually max and average pooling are the most popular. I'm not sure if anyone else has used any other function. So then out of this 2 by 2 patch, you pick the highest one, you come up only with one number. So then what that basically does is it cuts your x dimensions by half, your width by half, and your height by half as well. So you started with a 4 by 4, now you have a 2 by 2 output. So that basically reduced your size significantly.
So just
yeah, go ahead.
Just kind of philosophically the background there. So The convolutions, just so people are kind of clear, are how the neural net is picking out patterns, right? So it's identifying patterns in the image. The pooling, if you think of it, it's when you're pulling down those 4 pixels into just one, you're emphasizing the most important feature, or thing that's there, the most important pixel, right? That's actually got is the idea, if that makes sense. So you're first you're finding the pattern, and then you're isolating the pattern and throwing out the rest of the, if that makes sense.
Mm-hmm.
Right.
Yeah, and especially makes sense in this particular context if you think of it as a detector.
Right.
Because you're being asked at the pooling, you're asking, does this region contain the thing that I'm just trying to detect? And
Exactly.
then you're successively reducing the size of the image in this pooling to simplify the representation that gets fed eventually into the fully connected layers.
Yeah. Yeah, if you follow the latest papers by the godfathers, by Hinton, he will always complain that this is actually a breaking point for deep learning. He's not a big fan of pooling simply because you throw away stuff. But yeah, I guess this is version 1.0. Let's see where it takes us. Then how do you actually make this work in code in TensorFlow? You remember we started again with the sequential model, which is basically a stack of layers. We saw previously a flattened and dense layer. Now we have something new called tf.chaos.layers.conv2d. And this conv2d is basically a 2D convolution simply because our input is a 2D object. It has x and y coordinates. You specify something called how many filters, so what is the size of this convolutional layer. In this case, we're specifying 64 filters. In the previous image, we only saw 1 filter. This layer will have 64 filters. Each of them will be a 3x3. This is specified as a second argument. And one more thing that we didn't specify before is, let me go back. Once we do this, the next step to do is to add a bias here and also pass this through an activation function. So this is the new pixel value. You also add a bias here and you pass this new pixel value plus bias through an activation function. And that activation function here is a relu, which basically means keep only positive values, make everything -0. You specify also the input shape. In this case, remember this is 28 by 28 by 1. 1 is basically the channel complex, or the channel length. It's grayscale. It doesn't have a red, green, or blue channel. It only has 1. So what this will do is it will define 64 filters that will look at 3x3 patches of our image next to each other, and it will come up with a smaller shape from the 28 by 28. And that we can see that over here in the first output shape. So remember our image was a 28 by 28. Now it would be a 26 by 26 simply because we ignored the first row and the first horizontal row, the last horizontal row, the first vertical column, and the last vertical column. So basically we kind of stripped 1 pixel all around the image. So basically we lost 2 pixels horizontally and 2 pixels vertically. So instead of 28 by 28, we ended up with 26 by 26. And since we have 64 such filters, now we have 64 as an output now. So this is now a 3D object. Then the second layer we define is a max pooling layer. This looks at 2x2 patches and picks the maximum value. So remember we went from a 16 by 16 patch to a 4x4. So in this case, we go 26 by 26. We go basically to half the size of it, a 13 by 13. And this whole number will be the same as well. There's no parameters here to train, if you notice here on the last column, simply because this is just picking the maximum. There's no variables here. Then the output of this conv max pooling layer, we pass it through another convolutional max pooling layer with 64 filters. It will be different than the 64 filters based on weight initialization and how the model trains them. They just happen to be 3x3, and activation function is relu again. Another 2x2 max pooling layer. And when we do that, from a 13 by 13, we go to 11 by 11. Again, we drop 2 pixels. Then we halve them from the max volume, we go to 5 by 5, and we floor that in if this is an odd number. Then at the end of the day, we come up with 1600 numbers. So somehow we represented our 28 by 20 image to 1600 numbers. Then we pass that through a dense network to a dense layer, and the final dense layer, which is the output layer, 10. Yeah, this image is the same, just emphasizing on convolutional 2D versus max pooling 2D. And as I mentioned before, if you try different filters, there's a link here on the slides I was on the course. If you try different filters, you're going to get different features detected, like horizontal features, vertical features. You can sharpen the image, or you can detect, you can blur it. You can detect different features basically based on how you define these filters. And the whole point of the network is, let's use gradient descent to find filters that basically are able to map the inputs to our labels. And we have 64 of them in each layer. Mathematically, if you want to look at how you do that multiplication, this is just a basic arithmetic here of doing the patch and the filter, multiplying it. I don't think you're passing it through it looks like you're not passing it through a ReLU function here. So this is just the linear combination of it. Then when I was looking at this, Lawrence also covers or refers to Andrew's courses on convolutional networks. I found these slides very interesting, like, okay, why are we doing this and why is it a good idea? And Andrew mentions 2 things why convolutions are pretty useful. One is called parameter sharing. So for example, if you remember, we mentioned the vertical lines. That vertical line could exist anywhere in our image. It could be in the beginning, in the middle, in the end. Ideally, you want a detector or some kind of a filter that can detect that vertical line wherever it is. That way, you're not defining a filter for different parts of the image. You can simply scan your image and apply that filter, row by row and column by column, so that hopefully you'll detect it at some point. That's number 1. And number 2 is, in your fully connected layer, the layer to the right connects to all the inputs to the left. You have many connections. In convolutional networks, you don't do that. If you look at 3 by 3 patch, the output of that 3 by 3 patch only depends on that 3 by 3 part of the image. You completely ignore the rest of the image. So this output here, the green output 0, only depends on this 3 by 3 patch. This output 30 here, the red one, only depends on this 3 by 3 patch. So you have less connections. That's why if you paid attention to our shapes, the number of parameters are much, much less. When you go to the dense layers, that's when the number of parameters just takes off. It's significantly higher. Then if you look at this from an architectural perspective, you have your image. It could be, in this case, it's 28 by 28. In our case, in this case, it looks like a high definition image. You do a convolutional layer, you do another convolutional layer, and max pool, sorry. Convolutional and max pool, usually they go together. Convolutional max pool, they go together. Convolutional max pool, they go together. Then you have your fully connected layers. Then you have your output. Then you predict, using the loss function, you see how far your predicted value is from the label. You add them up, you come up with your cost function. And your whole goal as a network is to minimize this cost function.
George?
Yeah.
So it's basically each time you go through the convolutional layers, you're just trying to make it less complex each time you go through them. Each time you go through. Basically.
Yeah, exactly. You're looking at the same image. You're looking at the same image from 64 different perspectives. Think of it as like, if I give you a new product, and you have like a user group, and there's 64 of them, each one of them will look at that from a different perspective. But the network is trying to figure out which subset of my user group will actually map my input to my output the best. Yeah. And later on, we'll go through how does the image transform from input to the first layer, to the second layer, to the third layer. How does it look like? That'll be able to give you a better idea.
Oh, okay, thank you.
I think I suppose you could characterize it as making it less complex. But another thing earlier we talked about feature extracting. You know how when you're scanning, you know you're looking for the most important things. And what you see in these things is that it, you know, at the lower levels it picks up very lower level features, you know, vertical lines and moving things and, you know, stuff like that. And then as you move through the convolutions, they move through higher levels of abstraction is the way they talk about it. So, you know, you'll start out with lines and then maybe you'll move to ears and then eventually you'll get to, you know, a face or a cat or something like that. So I think that's kind of a miracle to me, you know, the way that works. But
yeah,
that's another way of thinking about it.
Thank you, Martin.
Awesome. Yep. Actually, the next slide is the one that I wanted to take a look at. So what we're looking at here, and we'll look at a collab version of this as well, is 3 different images of ankle boots. This is 1, this is 2, this is 3. And this is the output of the first convolutional layer. This is the output of the max pool layer. This is the output of the second convolutional layer. And this is the output of the second pool layer. And you can tell that by remembering that the input is a 28 by 28. After it passes to the first convolution, will be a 26 by 26. Then the first max pool will be in half. It'll be 12 by 12. Then the second convolution will be minus 2 pixels, so it'll be 10 by 10. Then the second pool will be half of this, will be 5 by 5. And this is just one of 64 filters, what is called convolutional number in this collab. But if I look at one of the 64, this layer is really interested in, for example, it's not looking horizontal lines, it's not looking at vertical lines. It really likes kind of like 45-degree lines or some kind of like upgoing trend. And you can see that also here. It doesn't have to be, you know, mathematically a line. It could be some kind of feature that this filter is looking for. But in the end of the day, the network goes through these 2 layers, or this, if you consider convolutional max pool as 2, then it's 1, 2, 3, 4 layers, and it comes up with this 4 by 4 representation of this ankle boot. And again, this is another ankle boot. This is a 4 by 4 representation of it. This is another ankle boot. This is a 4 by 4 representation of it. And the goal of the network, the second part of the network, which is the dense part of it, is to take these 60 numbers of 4 by 4 and see how can they be mapped to our labels. And the label for ankle boot, I think, is 9. Cool. I know we are 8:33. I'd love to look at the collab if you don't mind together. Then maybe we can pause and maybe we can visit the 4th week, the next session, given that time constraints. Okay, I'm getting some thumbs up. Awesome. Okay, I'll minimize. Yeah, actually, the collab is the last part of week 3. Let's look at it and then we'll pause for this session. Awesome. So when I use this, I had to make sure that I use the GPU. Let me zoom in a little bit so you can see my screen. Simply because convolutional layers do take a little bit of a processing power. In the beginning, I'm not using a convolutional layer, so I'm going to skip this. This is where we're defining it again. We have our fashion MNIST, we have a 60K for our training data set, 10K images for our test data set. We have our sequential model of convolutional max pooling, convolutional max pooling. And in this case, we're using, again, 10 outputs, so 10 categories. That's why we're using this categorical reverse entropy. And we're just training this network for 5 epochs on the training images and the training labels. And you'll see from 28 to 28, we go 26 by 26, we half, 11 by 11, we half it. Then we go to the 1600 number. Now, there's a very specific formula that gives you this number. This would be how many weights and how many biases do you have for each one of these. So the easiest way to do is from this layer, for example. So you have 128 nodes, and then they go to 10. That means that for each of output, you're going to get 128 numbers, and there's 10 of them. There's 1 to 8 times 10 is 1280. Then you have 128 biases for 10 biases for each one of these nodes. That's why I get this 1290. So overall, we have about 243,000 parameters that we need to train. We do that through each one of these 5 epochs, and you see the loss value dropping 0.4, 0.2, 0.2, 0.2, 0.1, and the accuracy going from 84, 89, 90, 91, 91. And that's on the training set. Let's go through this intermediate layer, which we briefly talked about, but something cool you can do in TensorFlow that I haven't seen yet in, I'm sure you can do it in other platforms as well. I just saw it first in TensorFlow, is you can look at different layers of the model and you can consider them as outputs. So you can take that layer output and you can store that in a list. Then what you can do is you can take the same model, you can take its inputs as inputs, which is the image of 28 by 28. And you can take this list now of outputs and you can consider them as an output. So think of it as the same image now is passing through this model. We call this activation model. And now I don't have an output as I had before, which categorizes an item into 10 categories. Now each output is actually an intermediate layer. So it would be a convolutional layer, a max pool layer, the second convolutional layer, the second max pool layer. So if we look at, for example, a random test label 100, or the first 100 labels, then they look like this. These are labels, so these are numbers between 0 and 9. So if we're looking at label number 9, which is ankle boots, there's one here, there's one here, there's one here. If I find the indexes of those, there's the 0, the 23rd, and the 28th index. And if I look at them, they look like this. So there's an ankle boot, ankle boot, ankle boot. Then if I want to look at the output of these intermediate layers, again, the input is 28 by 28. If you remember, this activation model has the intermediate representations of this input. So this would be the first convolutional, this would be the first pooling layer, the second convolutional, the second pooling layer. And we do this for different images. That was looking at one specific filter. That was looking at convolutional number 1. Remember, I have 64 of this in my network. If I look at a random one, let's say convolution number 32, just out of curiosity, I'm not sure what it's trying to focus on. Maybe somebody can tell. I'm not really able to tell, but this is how it looks like. And again, all 64 don't have to make sense to us. They're mathematical representations of our input. This is convolutional number 63. Not exactly sure what it's looking for either. I see some lines here, but I also see some patches here that it's looking for. Then what I did is I said, okay, just give me all 64 convolutions or 64 filters, sorry, of the first layer, and give me how it looks like from that perspective, so that I can look at the first image. Again, I'm looking at one image, how it looks like from passing through the entire network. And then it looks like this one is looking at some kind of lower level features, horizontal 45-degree lines. This is looking at vertical lines, horizontal lines. I'm not sure what's looking at here. I'm not sure, again, the outside or 45-degree. For some reason, this convolution here is really fixated with the bottom part of it, but not all the entire bottom part of it, just the part where the sole is. This one is the upper part. I don't know, I just find it fascinating. This looks at the entire bottom of the shoe, just the part of the beginning of the sole. This one looks at both vertical and horizontal. I find that interesting, convolution number 35. So anyway, the list keeps going. This one specifically looks at, horizontal lines. It ignores everything else. Yeah, the interesting thing is if you do this, every time you do it, you will get slightly different numbers based on your weight initialization. Similar here, 60. So that was interesting. And then I grouped here together all 8 by 8. Zoom out a little bit. All 64 outputs of my model, so that this is basically the same input, but now visualized in 64 different ways. This one I wanted to group together here. It looks like a Tetris game, if anything else. Cool. Then what I did is, then I looked at 3 of them instead of 1 by 1. I look at 3 at a time, but I don't want to show you all this. There's too many of them. I'm thinking of visualizing this in another way. I just wanted to show you other items here as well, instead of just ankle boots. So maybe we can look at 0. Label 0 is t-shirt top, how it looks like from just one convolution layer. So these are 3 different images. Again, the rows are different images, and the columns are different stages of our model for only one specific convolution here. So we're looking at convolution number 1 for this layer, convolution number 1 for this layer as well. We're only looking at one of the 64 filters for each layer. The label 1, let's see what label 1 for, which is trousers. So let's see what the first filter is looking at. Not sure. Again, the yellow parts are the highlighted ones. Not sure what it's looking at. The belt area, I'm not sure. Label 2, pullover. One of them had actually some characters. It really likes the right shoulder, if for some reason, and I'm not sure what this part here is, the bottom part. Then if we look at dresses, again, shoulder and a little bit on the left. Coat. Yeah, this filter is really fond of shoulders, I guess. Shoulder filter. Sandals, the upper part of it maybe. Shirt. Yeah, something similar. Sneakers. I like the flip here. Again, maybe 45 degrees lines. Bags. Not clear. And shoes or ankle boots that we saw before. So that was interesting to see how does our data look like as it transforms, as it traverses our network, and how does it look like one in out of many, many, many different ways that our network is shaping. I found that very interesting. We go back to our presentation. Questions about this? This was very interesting. Actually, this took me the longest to work on and put together, simply because I was so curious on what does this filter look like? What does this layer look like? So I was just fascinated by it. Awesome. Cool. Did you get so far, David, Robert? Did you do this lab?
I completed the whole course. Yeah.
Nice.
This was the part that I really wanted to do, and just figured I would go through and get to the next week instead. But it's on my bucket list for this weekend, I guess.
Got it. Awesome. Awesome. Okay. Then I think we'll pause here. It's 8:45. Next week we can visit the last week, and also the trivia, simply because the trivia has parts from all 4 weeks.
Sure.
I will skip the week 4 for now. The slides are there. I'll skip it for now. I'll go back to some questions I had. Maybe we can discover them together. So one of them was the JavaScript part that you mentioned, David. When you try to submit exercises, like you had to comment it out. The other one was
I think people had questions about why you normalize by dividing by 255, the pixels.
Is that what they're asking? Okay. Is the upper right hand image the same but just shown with different samples? Upper right image.
Oh, yeah.
I'm not sure what that refers. If you're looking about the pipeline, that's the output of the second pooling layer. So we have a convolutional pooling. That's the output of the second pooling layer, Bruce. Then a question that popped in my mind was, in the beginning, I wasn't giving flatten any default input shapes and it was working okay. But today when I tried the same collab, the same exact code, I was getting output shape, not share, multiple. I Googled it a little bit. Looks like I had to specifically mention the input shape. I would think that flatten would be able to figure out on its own, but for some reason maybe it wasn't able to. And
flatten is able to figure out shapes on its own when it's an intermediate layer, but I thought when it's the first layer you have to put in the shape. Is that right?
That was my understanding.
Good question. Yeah, I don't know. Let's look it up. Then when you do pooling and your dimensions are odd, you divide by 2, then you floor it. Do you lose anything there? Is the question. Do you lose one of the outer strips? Does it impact anything? Maybe, maybe not. I wasn't sure. Then one of the exercises when you did the manual convolution had something like range 1 to size -1. I was playing around with it, and if you do range from 1 to 3 in Python, you get numbers 1 and 2. So it looks like here you're actually going 2 pixels down instead of just 1, and I wasn't able to figure that out. Then, yeah, I'm interested in figuring out what
size X is 512, then 511 is actually the last pixel because it's 0 to 511.
Sure, that's 0 to 511. Yeah, I understand that. So size X would be 512. So then this would be 1 to 511, but this is range, and what that does is it completely ignores the last part. So this would be 1 to 510.
Was this when you were applying the convolution?
Yes.
Because you want to skip the first and the last pixel because you have a 3x3 to apply, so you can't apply it to the edges. So you start at 1 1 and you go to
510, I guess, right?
Yeah.
Got it. Okay, that's fine. Okay, so 1 to 510. Okay, got it. Okay, so Bruce is asking another question. We looked at different clothes. Did the upper right hand image the same for each garment? Bruce, I'm not sure I understand your question. If you don't mind just unmuting yourself and asking it, I'd be happy to go over it.
Can you hear me?
Yes.
Oh, okay. So when you went through, yes, this upper right-hand image, the 4x4, that's for this shoe, this ankle bootlet.
Yes.
And then you went to the trousers. Then you went to the, each garment you went through. Shouldn't we be looking at that region and see how it responded different for each garment? Wouldn't that be our interest?
Yeah, we could, but also remember that the label is different for each garment. So a region, let's say a lower region here being highlighted for ankle boots might mean something, but the same region highlighted for trousers might mean something else. That's my understanding.
Okay. Yeah, it'd be interesting to see each of the garments and what that region would show, because that's where we're going to get the classification from that upper right hand right.
Yep.
So the distinction, I think, would be for each garment what that pattern would look like and how we would put it into the 10 classes.
Yeah.
See, right now we're all looking at the same ankle boot, and they're all going to supposedly give us the same class.
Yep. Yeah, I imagine ankle boots will look something like this after the second layer. Maybe the trouser will look something completely different, a different combination. The shirts would look like a different combinations. Yeah, that's my expectation as well.
Yeah, okay, that's what I was trying. So I was trying to think of how, if you're looking to see how it pulls out the class, you'd want to see those next to each other, not necessarily boots next to each other.
Got it. Yep. I understand what you mean.
Okay.
Yeah, I
all
think
right.
one visualization that might be interesting would be to take all the ankle boots in the data set, average them together, and see what that looks like on the 5x5s.
Yeah.
All the trousers in the data set, see what they look like there.
Yep. And then what Bruce is saying, okay, now if I look at that average, how do the averages compare to each other? Are they completely different? Do they have something in common? Maybe sneakers and ankle boots have something in common. Maybe.
Yeah, I mean, maybe that's one way you could look to see if you could gain some intuition for what the network is actually doing.
But remember, you're 4 levels in the network. There are 2 more layers after this. But yeah, I would imagine sneakers.
But this is the last convolutional layer, right?
Yes.
So as soon as you get to the dense layers, it's going to be really difficult to see anything, visualize that.
This will be stripped out. This will be 1 long vector, 16 long number vector.
Mm-hmm.
But
Thank you.
Yeah, maybe as a exercise, we can look at that. There's only so many combinations I could try in 1 week. Okay, then in terms of callbacks, curious to see what other callbacks methods are there instead of just on epoch, and maybe I'm sure there are other ones. I've seen a few. And then the discrepancy or the difference between accuracy and loss in callback and calling them by the corresponding names. The issue that I mentioned with Tensor Board not showing graph, I'm not able to figure this out yet. If somebody is able to figure out, please let me know in Colab how do you make Tensor Board work. Something maybe I was interested in looking at is, okay, we saw how it looks, how the image looks like after each layer, but can we figure out how long does it take for the image to go to the next layer, like some kind of a execution time, or how complex is a layer? I don't know if TensorFlow can do that. I know it gives you times per each epoch. I don't know if it gives you time per each layer. Then there was a quiz in the course that says that applying convolutions on top of our deep neural network, the 2 dense layers, will make training, and I think the answer was faster, slower, and it depends on many factors. If those were my only 3 answers, faster, slower, it depends on many factors, I would say slower. I can't imagine a scenario where your convolutional adding convolution makes it faster, right?
I think it really depends on what you mean by that question, because when he took the week 2 dense network and then added convolutional layers in front of it, one of the points that Lawrence made was that, hey, this is going to take longer to run an epoch now. But at the same time, it actually converges and gets to a higher accuracy faster overall. So yeah, I too was confused by the wording of that question.
Yeah,
a little bit ambiguous.
Yeah, if you're looking at execution time, I agree with you. If you look at other parameters, of course, there's so many dimensions you can go. But if you look at just time, I would say 100%, no matter what you do, it'll always be slower. You're adding another layer, another complexity, right? Then if you look at all these models that we look at, and given from a high level perspective, given an input and an output, like what is the simplest model that can classify this data? Do we need 2 convolutionals and 2 max pool and a dense? Do we need 1? Do we need 3? What is the simplest model we can come up with to have decent accuracy? That's I think more like an open question, or more like an experience question, or hyperparameter tuning question. But I'm always interested in that. And then the last one is, maybe some of us can get together and online and figure out how to do one special session on just these optimizer loss and metrics combinations, because there's so many of them. Maybe each one of us can focus in on different loss functions, different metrics. I see these questions coming all the time whenever we talk about deep learning, like everybody, okay, when should you use this? When should you use that? I have some idea based on what I've read. I'm curious if we can just group that into one nice, interesting session. Then I'll end up with these resources. This course mentioned this machine learning fairness. Has a link here of how does our training data actually introduce bias to our model. And it's a very quick YouTube video. Check it out. It's very interesting. another one is this cool application from TensorFlow where Zimbabwe, where is it, or Madagascar? There's a challenge there with the cassava plant, and it's a plant that it's used like, think of it like a potato for us. The roots of this plant that you see here are used as the main ingredient for over 1 billion people around the world. And one of the issues they have over there is how to detect when a cassava plant is actually impacted by a disease.
So
And
here in the U.S., it's most commonly called yucca.
Yucca, okay.
Latin.
Yeah. But it was an interesting application where somebody actually labeled. That's the challenging part, right? You need supervised learning. You need to label healthy and unhealthy plants. And then they developed this app on a phone, which I guess we'll see with TensorFlow.js. And you can classify it if it's healthy or not. And then the app, you can ask for help or support near you. That was an interesting application of deep learning. Then to finish up, some meetups that either have happened last week or are going on later this week. Looks like most of them are going on later this week. This one happened, I think, a day or two ago. I have links for all the meetups here. It was focused on features of TensorFlow. There's a YouTube recorded version of it. There's one that I found somehow recently. It's on April 17th on recommender systems and deep learning. A data scientist from Etsy will talk about how do they use deep learning to do recommendations for different products when you buy something on Etsy. Then very often is in our group on April 25th, they have another meetup online. I think it will be covering medical images.
That's correct.
Yep, thanks, Rob. I forgot to mention that deep learning is also releasing a medical AI for medical purposes specialization. I have a link here as well. If you're new to Python, there's an online Python data science program on this meetup here. If you're into healthcare, I know some of our members here are practicing healthcare. There's a new meetup. I'm not sure it's from a deep learning or AI perspective. I think it's more from an analytical or data analysis perspective. If you prefer reading books instead of looking at something online, and there's an online book club that looks at Facebook and the story of Facebook. Thinkful and Flatiron are bootcamp companies throughout the country, and they have 2 sessions coming up. There's one on cybersecurity and an interesting one on Yellowbrick, which is a Python library for machine learning. It allows you to peek into your machine learning problems or machine learning models and see how they behave and hopefully get some kind of interpretability. I think it's mainly focused on machine learning. I attended the session they had in DC a couple of months ago. I found it very interesting. The GTC is still going on, and I just want to mention this TensorFlow certificate that's out there again. And we'll do this next week, the quiz. That's all I had. So next week, maybe we can focus on week 4 and the quiz and any questions that we have in the meantime.
Really great job, George.
Awesome. Thank you. Thank you, Martin.
Yeah, thanks a lot,
Yeah,
George.
thank you.
It's really good.
Awesome. Any questions, feedback? Open floor, everyone. Welcome, Bruce. Okay. Then I'll stop the recording here. Thanks everyone for attending. I'll post it online and be on the lookout for the next session. We should finish week 4 and then we'll continue with course number 2. And if you haven't joined our Slack community, again, there's a link on our meetup. Feel free to join it.
And the slides are on the Meetup announcement page, just for people that are asking.
Yes.
Good night, everybody. Thank you.
Yeah,
Thank you.
Good night, Kathleen. I'm just going to show the Meetup page here so you know where it is. Sorry, I went to GitHub, which has a link to our Meetup. So you'll see the first session on April 3rd, and today's session. So here you'll see the presentation. I have a link here for the trivia game. If you can wait until next week, that'd be awesome. And also the links to the previous meetup. But everything is here on the meetup page. And the only thing that I'll be posting is the recording, hopefully tomorrow. It'll be in this section here. Awesome. Let me stop sharing.
Thank you, George.
Thank you, everyone. This was awesome.
Yep.